Hello, I'm N J Wildberger, and today we're going to introduce the second most important problem in linear algebra. The context is that we have now two frames of reference instead of one. We've been talking about setting up a coordinate system with basis vectors E1, E2, perhaps E3 if we're in 3 dimensions, and then using those basis vectors to represent other vectors, and then ultimately to represent linear transformations via matrices. That's all very important, and I hope you've mastered the essentials of that. Now we're going to move up a step and consider what happens when we have two different frames of reference. This is a very common thing in practice because let's say you're making a movie about something. You may have a basic frame of reference that is the basic camera. Then you may have an actor moving around inside that frame who's constantly moving around, and his frame of reference is different from the reference frame. So we're going to go back to our friends Bob and Rachel. Here's our two-dimensional affine plane with two sets of coordinates. A blue frame representing Bob and a red frame representing Rachel. So here are Bob's basis vectors E1 and E2, and he uses those two basis vectors to measure everything in the plane. So he measures vectors with respect to E1 and E2, and he represents linear transformations via matrices depending on E1 and E2. Similarly, Rachel measures everything in terms of her basis vectors, which are F1 and F2. She measures vectors with respect to F1 and F2, and she also measures linear transformations with respect to F1 and F2. And what we want to do is we want to compare how Bob's and Rachel's measurements are related to each other. So just for some preliminary notation, let's let xb and yb represent the coordinates of a vector with respect to Bob. And let's let x sub r and y sub r be the coordinates of a vector with respect to Rachel. So for example, the vector v, which is from here to here, in Bob's framework that would be measured as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in the E1 direction and 1, 2, 3, 4, 5 in the E2 direction. So Bob would give that vector a coordinate representation 10, 5. On the other hand, Rachel would say, well, to go from here to here, we take 2 steps in the F1 direction, so 2F1 plus 1F2. So she would represent it by the vector 2, 1. These are two different ways of representing the same vector. One in Bob's system, one in Rachel's system. Natural question is, how would you go from one to the other? If you knew one of them, how would you find the other? Well, you might guess from looking at these two that what you do in this case is you divide by 5. Well, that's not correct, as you can see from looking at another example. Suppose we consider the vector u, which is from here to here. Bob would measure that as 1, 2, 3, 4, 5, 6, 7, 8 in the E1 direction, and 1, 2, 3, 4, 5, 6, 7 in the E2 direction. So he would represent it by the vector 8, 7. On the other hand, Rachel would represent that as 1 times F1 plus 2 times F2, so she'd represent it by the coordinate vector 1, 2. So dividing by 5 is not how we go from here to here, it's a little bit more subtle. To figure out how to go from one of these representations to another, let's look at the relationship between the two basis vectors. So F1 is in Bob's system 4E1 plus E2. And F2 is in Bob's system 2E1 plus 3E2. So this little box here tells us what F1 and F2 are in terms of E1 and E2. We can write that information in a matrix form by creating a little vector. Just F1, F2 equals 4, 1, 2, 3 times E1, E2. Now the meaning of the variables E1, E2 here is different from the usual meaning. In this case, these guys are actually vectors. So this has a different interpretation from other systems that we've written like this. But nevertheless, the fact that these two objects have a linear relation can be used to invert them. In other words, we just multiply by the inverse of this matrix to find that E1, E2 equals, there's the inverse, times F1, F2. If we write that out, we see that E1 is 3/10 of F1 minus 1/10 of F2, and E2 is minus 2/10 of F1 plus 4/10 of F2. Let's see if that makes sense pictorially. So what it means is that if Rachel was looking at Bob's basis vector E1, she would express that as 3/10 of F1. So there's F1, so 3/10 would be maybe up to here. There's 3/10 of F1. And then subtract 1/10 of F2. Well, there might be 1/10 of F2 in this direction, just 1/10. So we're talking 3/10 of F1 minus 1/10 of F2. That is indeed pretty close to what we see E1 is. And similarly for E2. So this is the relationship between the two sets of basis vectors. Bob's basis vectors, Rachel's basis vectors. Now let's see if we can use this to relate the coordinates of a given vector with respect to Bob and Rachel. So suppose we have a vector v, and its coordinates with respect to Rachel's system are x sub r and y sub r. What does that mean? It means that the vector is x sub r times f1 plus y sub r times f2. These are Rachel's two basis vectors. Now we've just seen what f1 is in terms of Bob's basis vectors. It's 4e1 plus e2. And we've seen what f2 is. It's 2e1 plus 3e2. So we can replace f1 and f2 by their representations in Bob's system. And then when we expand this out, group all the e1 terms together and all the e2 terms together, then we get 4xr plus 2yr times e1 plus xr plus 3yr e2. And this means that, according to Bob, the coordinates are this and this, which we can write as a vector like this. So there's Bob's x-coordinate, Bob's y-coordinate. And we see that Bob's x-coordinate is 4xr plus 2yr in terms of Rachel's x and y coordinates. And Bob's y-coordinate is x sub r plus 3y sub r. So this is the relation that we were after. This is the relation that tells us how to go from Rachel's coordinates for a given vector to Bob's coordinates for that same vector. And we can rewrite this in matrix form by saying that the vector xb, yb, that's Bob's coordinate vector, is Rachel's coordinate vector times the matrix 4, 2, 1, 3, the matrix of coefficients over here. So this important equation relates Bob's coordinates for a vector with Rachel's coordinates for a vector. In fact, it's a way of starting with Rachel's and getting Bob's. We can also invert, because there's a symmetry between Bob and Rachel here. So we can invert this relation by dividing by this matrix. If we divide this by this matrix, that's the same as multiplying by the inverse. Then we multiply by the inverse on this side, and then xr, yr is all by itself. And it equals the inverse of this matrix, which is right here, times this vector. And then when we read off what each line here says, it says that xr equals 3/10 xb minus 2/10 yb, and y sub r equals minus 1/10 xb plus 4/10 yb. So these two are complementary. This is expressing Bob's coordinates for a vector in terms of Rachel's. This is expressing Rachel's coordinates for a vector in terms of Bob's. Let's introduce now a little bit of notation that will make it easier for us to talk about this change of coordinates business. We've been talking about Bob and Rachel as two individuals, but mathematically they are represented by their basis vectors. Bob has two basis vectors, which are the basis for his framework. Rachel has two basis vectors, which are the basis for her framework. And it's really those two basis vectors that capture all the information, and those basis vectors in a particular order, namely E1, E2, and F1, F2. So let's say that this basis in that order is what we call B. So instead of Bob the person, we're going to think of B, the ordered basis consisting of the vector E1 and the vector E2. And instead of R being Rachel the person, we're going to think of R as being the ordered basis F1 and F2. Now I use this list notation instead of set notation because the order really does matter here. When you use set notation with curly brackets, it means that order does not matter. List with square brackets means that order does matter. So these are two ordered bases. And now we can introduce the following notation. Suppose we have an arbitrary vector v. We can express it in terms of the vectors in the basis b, say x e1 plus y e2. In that case, we'll say that the coordinate vector for v with respect to b is the vector with coordinates x and y. That's the coordinate vector for v with respect to the ordered basis b. And that same vector could also be written in terms of f1 and f2 with different coefficients, say z and w. Then we would say that the coordinate vector of v with respect to r is the vector zw. So the same vector v can be represented in different ways depending on the basis that you choose to set up your system. V sub b is the coordinate vector of v with respect to the basis b. V sub r is the coordinate vector of v with respect to the basis r. Then the relationship that we've established on the previous page is exactly this one. That v sub b equals the matrix 4, 2, 1, 3 times v sub r. In other words, to get Bob's coordinate vector for a given vector v, we take Rachel's coordinate vector for that vector and multiply by that matrix. And on the other hand, if we start with Bob's coordinate vector and we want to get Rachel's coordinate vector, then we're going to have to multiply by this matrix, which is the inverse of that one. And let's give this matrix or this matrix a name because it's really helping us change basis. So we'll call it a change of basis matrix. And we'll usually use C for it, for change. And we'll put little subscripts under there when needed to clarify to ourselves that this matrix here is helping us go from Rachel's basis to Bob's basis. In other words, given Rachel's coordinate vector for something, we get Bob's coordinate vector by multiplying by this matrix. There it is there. And the other way around, CBR going from Bob's to Rachel's, that change of basis matrix is this one here. And these two change of basis matrices are inverse matrices. Okay, it's quite a useful idea that a matrix like this is representing a change of coordinates. In fact, that's how we started off this course, by thinking about matrices as change of coordinates. And I remember I said that going from here to here was essentially the most primary problem in the subject. And let's record also how we get one of these change of basis matrices. So the change of basis matrix CRB is obtained by finding the R basis vectors coordinates with respect to B and putting those down the columns. So for example, CRB, which was this matrix here, its first column was exactly what F1 was with respect to Bob's basis. In other words, Rachel's first vector was 4e1 plus 1e2. And the second column is the coordinates of F2 with respect to Bob's system. So F2 was the vector 2e1 plus 3e2. So to find the change of basis matrix C from R to B, we put R's basis vectors coordinates with respect to B down the columns. Alright, so let's just check now that this formulation does agree with our earlier observations that we started with. Suppose we consider the vector V, whose coordinates in Rachel's system are 2, 1. So the coordinate vector of this vector V is 2, 1 with respect to Rachel. Then according to our basic formula, the coordinates of V with respect to Bob should be given by this. Here's the change of basis matrix, exactly this one here. Here's the coordinate vector of V with respect to Rachel. When you've performed this multiplication, 8 plus 2 is 10, 2 plus 3 is 5. That was indeed the coordinate vector of that first vector V that we talked about with respect to Bob. So that's how you go from Rachel's to Bob's coordinate vector for a given vector. There was also a second example, which was U in the original problem, and its coordinate vector with respect to Rachel was 1, 2. And we could plug that into the formula. We get 4 plus 4 is 8, and 1 plus 6 is 7. So that's how we get Bob's coordinate vector for U from Rachel's coordinate vector for U. Alright, so we've got these two systems, these two frameworks for affine geometry, Bob's and Rachel's. And we've been talking about how to go from representing a vector in one system to representing that same vector in the other system. We've seen that there's a change of basis matrix that you multiply by, that takes you from the coordinates of one to the coordinates of the other. Now let's step up to a slightly higher level. And let's try to understand how linear transformations go from being looked at in one frame of reference to another frame of reference. Okay, in any one frame of reference, say Bob's, a given linear transformation, a rotation say, or a reflection, or a dilation, a linear transformation is going to have a certain matrix representing it. And that matrix is with respect to Bob's system, with respect to his choice of basis vectors E1 and E2. Now that same linear transformation, when looked at by Rachel, is also going to have a matrix associated to it. But it's going to be a different matrix to the one Bob has. So Rachel's description of a linear transformation as a matrix and Bob's description of that same linear transformation are going to be different. And we need to be able to see how to go from one to the other. It's a little bit more complicated than just multiplying by a change of basis matrix, but not that much more complicated. So let's start with an example. Let's look at a linear transformation which is particularly simple in Rachel's system. So we're taking Rachel's basis vectors, which are F1 and F2, and we're supposing we have a transformation which is a dilation, a mixed dilation in Rachel's system. What does that mean? Well, it means that it takes the first basis vector and multiplies it by some number. And it takes the second basis vector and multiplies it by a different number. In this case, the numbers happen to be 5 and 7. So in Rachel's system, such a linear transformation, which stretches the first basis vector by a factor of 5 and the second by a factor of 7, would be represented by this diagonal matrix, 5, 0, 0, 7. That represents that dilation, that mixed dilation. And what we're really saying here is that the linear transformation acting on V is this matrix times the vector. Everything in Rachel's system. So we're measuring the vector in Rachel's system. There's this matrix in Rachel's system. And there's the image vector in Rachel's system. So now what we want to do is we want to convert this to information about how the same linear transformation looks like in Bob's system. So we have to take this equation and replace all the things involving Rachel with things involving Bob. Okay, so let's start with the left-hand side. Let's look at T of V in Bob's system. Well, we know what T of V is in Rachel's system. So this is the coordinate vector of T of V. V is just some arbitrary vector. T of V is the image of the vector under the transformation. Here's the coordinate vector of that image in Rachel's system. To get the coordinate vector of the image under Bob's system, we need to multiply Rachel's vector by our change of basis matrix. And it's the change of basis matrix CRB. So that's TVB equals CRB times TV sub R. And now TV sub R is exactly this, so we can replace it with this. So we get CRB, A sub R, V sub R. Now we're going to replace this V sub R, which is the coordinate vector for the vector V in Rachel's system, with this right here. This is the coordinate vector of V in Bob's system times the change of basis matrix CBR, which converts Bob's coordinates to Rachel's coordinates. So take Bob's coordinates, multiply by this matrix, then you do get Rachel's coordinates. When we rewrite that as simply A sub B, then we have something that looks exactly like this except with Bob's system. TV of B equals some matrix A sub B times V sub B. And this matrix A sub B is Bob's matrix for the linear transformation, because it tells us how to go from a vector in Bob's system to the image of that vector, also in Bob's system. And I point out here that this matrix here and this matrix are not the same. This one is the inverse of that one. So we've obtained the formula we were after. The formula that allows us to go from Rachel's matrix for a linear transformation to Bob's matrix for that same linear transformation. And the formula is that A sub B equals C sub RB times A sub R times C sub BR. And perhaps it's easier to remember if we write it in this form. A sub B equals C times A sub R times C inverse, where C is this change of basis matrix CRB. So let's go back to our specific example that we had. Remember, we started out with this dilation in Rachel's system that had this as its matrix, 5007. Here is the change of basis matrix, CRB, and here is its inverse. So let's multiply those three matrices together and see what we get. The 1/10 can come out here. Now let's have a look at just the product of these two matrices, which is a little bit interesting and important to see what happens. We're multiplying this rather general matrix with a diagonal matrix on the right. So the diagonal matrix is on the right. And what happens is, well, let's do the multiplication. 4 times 5 plus 0, so that's 20. And 5 times 1 plus 0, that's 5. The first column is obtained from the first column here just by multiplying by 5. And the second column here is 0 times 4 plus 2 times 7, that's 14. 0 times 1 plus 3 times 7, that's 21. Obtained from this second column by multiplying it by 7. So if you have a matrix and you're multiplying it on the right by a diagonal matrix, then what happens is that each column gets multiplied by the corresponding diagonal element. Okay, good. Now we still have to multiply by this 2 by 2 matrix. I'll let you do the multiplication, you get that, which can be simplified a little bit to there. And so that's the matrix for that linear transformation in Bob's system. In other words, as far as Bob is concerned, Bob only has his coordinates, x and y. He thinks that a vector with coordinates x and y goes to what happens when you multiply by this matrix. In other words, 23 over 5 times x plus 8 over 5 times y, that's the first entry, and minus 3/5 x plus 37/5 y. You can see that's not a diagonal matrix anymore. So Bob's form for this matrix is more complicated than Rachel's form. In Rachel's point of view, this particular transformation had a particularly simple description. In fact, geometrically, we can visualize this transformation much simpler in Rachel's system rather than in Bob's system. It's an important idea that a given linear transformation looks simpler in some frameworks rather than in another. A diagonal representation like this is particularly pleasant because it's very easy to understand geometrically what that transformation is doing. It's just stretching each coordinate direction by the amount on the diagonal. So what we've seen is that if a linear transformation is represented in two different frameworks, then the matrices for them are related in a relatively simple way, that you get one by taking the other and multiplying it on one side by some matrix C and on the other side by the inverse of C. That turns out to be a particularly pleasant relation, and it's worth a separate definition. So we say that two matrices A and B are similar, and we write A tilde B, precisely when A equals C times B times C inverse for some invertible matrix C. So if you can find some matrix C such that A equals this combination, then we say that A and B are similar. And our interpretation of this is that similar matrices represent the same linear transformation, but with respect to different bases. So here's an example. If you take this diagonal matrix 2, 0, 0, 3, and you multiply by this matrix, which is invertible, I'll let you calculate what that inverse is and calculate the product, then you get this matrix. So that means that this matrix and this matrix are similar. They don't look very similar, perhaps, and that's because this multiplying by C and C inverse on both sides can really change the matrix dramatically. But nevertheless, we'll see that these two matrices have a lot of common properties. And in some sense, they're pretty well the same, or they act in a similar way. This relation of similarity has a few pleasant properties that make it what we call an equivalence relation. So let me state what those properties are. First of all, if A happens to be C, B, C inverse, then we can invert this relation to express B in terms of A. How would we do that? Well, we would take this equation and we would multiply it on the left by C inverse. If we multiply this by C inverse and this on the left by C inverse, then this C inverse and this C become just the identity matrix, and then that essentially disappears because the identity times anything is anything. So that's the first thing. You multiply by C inverse on the left, and then you multiply by C on the right. Well, the C multiplying that C inverse will also give you an identity matrix, and you'll just get B on the right-hand side here. So you'll get that B equals C inverse AC. Now that looks almost like the same, and it pretty well is, if we rewrite it as C inverse times A times C inverse inverse. And that's allowed because the inverse of the inverse is the original matrix. Then we see that we have something of the form sum matrix times A times that sum matrices inverse. So this shows that if A is similar to B, then B is similar to A. And that property is called the symmetric condition. So we say that the relation is symmetric. The second property of similarity is called the transitive property. And that says that if A is similar to B and B is similar, say, to E, then A is similar to E. So A is similar to B, B is similar to E, then the first one is similar to the third one. And here's the proof. If A is similar to B, then we can write A equals C, B, C inverse for some matrix C. And if B is similar to E, then B equals D times E times D inverse for some matrix D. If we now combine them, we get A equals C. We replace the B here with that, D, E, D inverse times C inverse. And now remember, matrix multiplication is associative. You're not allowed to change the order, but you are allowed to change the bracketing. So instead of having the brackets this way, we can group C and D together. And we can group D inverse, C inverse together. And now we have to remember that D inverse, C inverse, that's the inverse of CD. There's a theorem we proved, that the inverse of a product is a product of the inverses, but in the opposite order. So once we've rewritten this in this fashion, we see that it's of the form sum matrix, the sum matrix being CD, times E times that sum matrices inverse. So conclusion, that A is similar to E. Then there's one third property which is almost so obvious it's not worth mentioning, but it's still important to mention it. It's that any matrix A is similar to itself. And that's because any matrix A can be written as the identity times A times the identity inverse. That's called the reflexive property. Now these three properties, the reflexive property, the symmetric property, and the transitive property, mean exactly that our notion of similarity is what's called an equivalence relation in mathematics. So now I can tell you what a generalized dilation is. A matrix is a generalized dilation if it's similar to a diagonal matrix. If it's similar to a diagonal matrix. So that means that A is similar to D, where D is a diagonal matrix. Or specifically, it means that A can be written as C times D times C inverse for some invertible matrix C and some diagonal matrix D. And geometrically what it means is that A represents a linear transformation which in some basis looks like a diagonal transformation, one that's purely stretching along the three coordinate directions. And now I can tell you what the second most important problem in linear algebra is, and one that will be indirectly or directly influencing a lot of the rest of the course. It's this one right here. How does one tell if a given matrix A is a generalized dilation? Now another word for generalized dilation is diagonalizable. So that just means exactly the same thing. How do we tell if a matrix A is diagonalizable? And if it is diagonalizable, so if we can write it as C times D times C inverse, where D is a diagonal matrix, then how do you find the diagonal matrix D? And how do you find the change of basis matrix C? In other words, how do you go back from how we started with a diagonal matrix and then we multiplied it on the left and the right by some change of basis matrix? We got a new matrix. So the problem is, suppose we started with a new matrix. How could we figure out what diagonal matrix we started with and what change of basis matrix we multiplied on the left and right by? Okay, so this is a very important problem with all kinds of important applications. And it's going to be a main topic for us. So let's have a look at the following example. Here we have a matrix D, a diagonal matrix, and we're conjugating it by this matrix C. That's the process of multiplying on the left by C and on the right by C inverse. So this is a matrix C, and here's its inverse, and when you multiply that out, you get this matrix A. So our basic kind of problem is, suppose we start with this matrix A, and we're not told that it comes about through this process. How are we going to find C and D? This is our basic problem. So here's the idea that allows us to solve this problem. We start with the equation A equals CD C inverse. So we assume that A can be written this way. And we rewrite this equation by multiplying on the right by C. So on the right by C gives AC there and equals CD there. So in this example here, there would be the matrix A, there's the matrix C, and that equals the matrix C times the diagonal matrix D. So let's have a look at what happens when we look at both sides of this equation. When we multiply C by this diagonal matrix D, we get the situation that we've talked about before, multiplying a matrix by a diagonal matrix on the right. And what happens is that the first column gets multiplied by the first diagonal entry, so it becomes 8, 12. And the second column becomes multiplied by the second diagonal entry, so it becomes -1, -2. So altogether, if we look on this side and compare it with here, when we multiply this matrix by this matrix, what we are doing is working column-wise. The first column here is obtained by taking this matrix multiplied by this first column here. So let me say that again. When we multiply this matrix by this, and we think about it column-wise, the first column of the result is obtained by taking this matrix times this column. So we have the situation where A times this column 2, 3 equals this column here. But we've seen that this column is just a multiple of 2, 3. It's 4 times 2, 3. So we're getting the situation where A times this column is 4 times this column. And the same thing happens for the second column. When we multiply A times the second column, we're getting the second column over here. And that's -1 times the column we started with. So again, we're getting the equation that A times some vector is a multiple of the vector. So in other words, we're thinking of C as being a mystery matrix. We're thinking of D as being a mystery matrix. We're given A. Then the crucial property is that the columns of C have the property that when you multiply them by A, you're getting multiples of them. So the two columns of C satisfy the equation A times V equals lambda times V for some number lambda. This is a very important equation, and it's this equation that allows us to find C and D. We're going to solve this equation for the vectors V and the numbers lambda. And the vectors V are going to form the columns of our change of basis matrix C, and the entries lambda are going to form the diagonal elements of our diagonal matrix D. So let's make two important definitions that capture that crucial equation. So if we start with a matrix A, then we say that a vector V, which is non-zero, satisfying A times V equals lambda times V for some number lambda, that vector V is an eigenvector for the matrix A. So given a matrix A, if we can find a vector V satisfying this for any lambda, then that V is an eigenvector. With the stipulation that eigenvectors are not allowed to be zero, because the zero vector always satisfies this. So we're not going to include that. And then, associated with that, the number lambda that appears in this equation is the associated eigenvalue. So the vector is the eigenvector, that's the vector V, and the number lambda is the eigenvalue associated to the eigenvector V. And we saw in the previous example that a given matrix A can have several eigenvectors. And for each one of those eigenvectors, it's going to have an eigenvalue. So here was our example. The matrix A is 19, minus 10, 30, and minus 16. Now you can check that if you multiply A times the vector 2, 3, what are you going to get? Multiply by 2, 3. So you're going to get 38 minus 30, that's 8, which is 4 times 2. And the second entry will be 60 minus 48, that's 12. That's 4 times 3. So the vector 2, 3 has the property that when you multiply it by A, you're getting exactly 4 times 2, 3. You're getting a multiple of 2, 3. So the matrix A, if you think of it as a linear transformation, it's stretching the vector V equals 2, 3 by a factor of 4. So that's an eigenvector for the matrix A, and 4 is the associated eigenvalue. But this matrix A has another eigenvector, namely the vector 1, 2. If we multiply by 1, 2, we get 19 minus 20, that's minus 1, which is minus 1 times that entry. And the second entry will be 30 minus 32, that's minus 2, and that will be minus 1 times this entry. So the matrix times 1, 2 is minus 1 times 1, 2. So this is another eigenvector for the matrix A, and its associated eigenvalue is minus 1. Are there any other eigenvectors for this matrix A? Well, there's one way of finding other eigenvectors is simply to take an existing eigenvector and multiply it by any non-zero number. So if we took that eigenvector and multiplied it by 10, we would get another eigenvector. Okay, but that's a kind of a trivial thing. So eigenvectors are only determined up to a scale. But other than that, it turns out that this matrix only has these two as its eigenvectors. There's a summary of it. The matrix A has these two eigenvectors, say V1 equals 2, 3 and V2 equals 1, 2, with associated eigenvalues lambda 1 equals 4 and lambda 2 equals minus 1. And our notation is organized so that this eigenvalue goes with this eigenvector, and this eigenvalue goes with that eigenvector. Now I pulled these things out of a hat. I just said, hey, look, these two vectors happen to have this property. But how did I get these vectors? How could you get these vectors if you didn't know them beforehand? So this process of finding the eigenvectors and the eigenvalues of a matrix is a very important process. And so let me show you how it goes in the 2 by 2 case, which is pretty indicative of the general situation. There's a number of steps. And the logic of it is quite interesting, and it's important to follow the argument. So let's return to the matrix A that we've been considering just in that last example. There it is there. 19, minus 10, 30, minus 16. And we pretend we don't know what the eigenvectors are, and we want to find them. So here's the equation that we need to solve. There's the matrix A. There's some vector V. And we want to solve that product equals lambda times V. So not only do we not know x and y, but we also don't know lambda. So we actually have 3 unknowns floating around in this equation. Let's write out each of these equations. There are 2 of them, just to orient ourselves. And let's bring everything to one side. So the 19x minus 10y equals lambda x. We'll bring the lambda x to the other side so that it's 19 minus lambda x minus 10y equals 0. That's the first equation. And the second equation, which here reads 30x minus 16y equals lambda y, we'll bring the lambda y also to the other side. So that reads now 30x plus minus 16 minus lambda times y equals 0. Okay, that's a little system of linear equations in x and y. It's a 2 by 2 system, with the right-hand side being the vector 0. And let's just write that out in matrix form. The coefficients are 19 minus lambda, minus 10, 30, and minus 16 minus lambda. So that's the matrix times xy equals 0, 0. And this matrix we could have just concluded immediately from here. What it is just the matrix A minus lambda times the identity. You see the lambdas are only appearing along the diagonal, so we're really subtracting lambda times the identity from the original matrix A. That's what that matrix is. All right, let's think about this equation. We have some matrix times some vector equals 0, 0. We're trying to solve for x, y, but a slight complication is that we don't know these actually as numbers. There's some lambda floating around here on the left-hand side. Okay, there's one obvious solution to this, independent of what lambda is. The obvious solution is that x equals y equals 0. Okay, that's an obvious solution, but it's not allowed because we're not interested in that obvious solution. We said an eigenvector is going to be a non-zero vector. All right, now let me make the following important observation. That if this matrix is invertible, if it has an inverse, then we could take this equation and we could multiply both sides by that inverse matrix. And what will we obtain? We would get xy all by itself equals the inverse matrix times 0, 0. Now I don't care what that inverse matrix is. If you multiply it by 0, 0, you're going to get 0, 0. So if this matrix is invertible, then we can solve this system and we get xy equals 0, 0. In other words, there's only one solution in that case. There's a very important little argument here. Let me say it again. If this matrix is invertible, then in fact this system only has the solution 0, 0, which we're not interested in. So the only way this system has a solution that we are interested in is if this matrix is not invertible. It must be not invertible in order for it to have a solution that is non-zero. So we require this matrix A minus lambda I to not be invertible. And when is a matrix not invertible? Precisely when its determinant is 0. So remember, a matrix is invertible precisely when its determinant is non-zero. So this is a situation where we want this matrix to be not invertible, and so we require that the determinant of A minus lambda I be 0. And now we're going to see that this is a quadratic equation in lambda in this case, and we can solve that quadratic equation for lambda. So what we're actually going to do is we're going to find lambda before we find x and y. Our first step is to find the eigenvalues. So let's have a look. What does this equation, called the characteristic equation, look like? So here's that determinant that we need to calculate. The determinant of this 2 by 2 matrix. So it's that times that minus that times that. There, plus 300. We expand that out, we get a lambda squared. We get 19 times minus 1, that's minus 19, plus 16, that's minus 3 lambda. And the constant term, there's a minus 19 times 16 plus 300. Well, 19 times 16, I worked it out over here, that's 304. So it's minus 304 plus 300 for a total of minus 4. And conveniently, this quadratic expression factors as lambda minus 4 times lambda plus 1. And so when is this thing equal to 0? It's equal to 0 when lambda equals 4 or lambda equals minus 1. So those are the only two values for lambda that will make this matrix not invertible. Not invertible. These are the eigenvalues of the original matrix A. Now for each one of these, there's an associated eigenvector. And how do we find that? Well, let's do it individually. So that lambda equals 4, let's look over here. Here is the equation that we're trying to solve. We have A minus lambda times V equals 0. V is the vector xy. And lambda happens to be 4. So A minus 4i, you just plug in 4 here, and you get the matrix 15, minus 10, 30, and minus 20. That times xy equals 0, 0. Now if you stare at this, you'll see that the first equation is actually the same as the second equation up to a multiple of 2. So although it looks like there's two equations, there's really only one equation. And that's what lets there to be a non-zero solution. It turns out that x and y is a multiple of 2, 3. So if x is 2 and y is 3, then we get 30 minus 30 equals 0. And there's a parameter because you can take any multiple of 2, 3. That's the eigenvector associated to the eigenvalue lambda equals 4. And over here, the other case, when lambda equals minus 1, then A minus lambda I, this matrix here, becomes the matrix 20 minus 10, 30, minus 15. And again, this system, although it looks like two equations, really is only one equation because the second one is just a multiple 3/2 of the first one. So there's really only one equation here that allows us to solve for x and y. It's a multiple of 1, 2. So the associated eigenvector to the eigenvalue lambda equals minus 1 is this vector 1, 2. And these are the two vectors that I pulled out of the hat on the previous page. And these are the multiples that you get when you multiply the original matrix A by these two vectors. So this is a very important derivation. Okay, please make sure you understand everything that I've done in this derivation because it's the fundamental argument for finding eigenvalues and finding eigenvectors. All right, so here's an exercise. First one, suppose we have two ordered bases, B and R, consisting of E1, E2, and F1, F2. And we're told that F1 is 5E1 plus 2E2, and F2 is 3E1 plus E2. Then first of all, express E1 and E2 in terms of F1 and F2. Secondly, write down the change of basis matrices CBR and CRB. Then use those change of basis matrices to convert from B coordinates to R coordinates or vice versa. So if a vector V has B coordinates 4 minus 2, find its R coordinates. And if another vector U has R coordinates 7 minus 1, find its B coordinates. And finally, suppose we have a linear transformation T which satisfies that it's diagonal in the R basis. So T of F1 happens to be minus 2 F1, and T of F2 happens to be 9 times F2. So find the matrix for T with respect to the basis R, and also the matrix for T with respect to the basis B. Second exercise, show that the matrix A, 0, 1, minus 1, 0, that was a rotation matrix, is not diagonalizable. Show that the matrix A with entries minus 1, minus 2, 4, 5 is diagonalizable by finding its eigenvectors and eigenvalues. And finally, if we define the trace of a matrix, say in the 2 by 2 case, to be the sum of the diagonal entries, that's the definition even for a larger matrix, the trace is always the sum of the diagonal entries. Then show that if two matrices A and B are similar, then their traces are the same. So in our derivation of the eigenvalues and eigenvectors, there was one step where I didn't completely explain what was going on. That was the final step where we were solving that final system, A minus lambda I times V equals 0. That's an example of an equation that we haven't talked too much about before. And it goes a little bit beyond the examples that we've been looking at up till now. So it's time for us to admit the deficiencies of the inverse approach to solving systems. Writing down inverses of matrices is fine for the 2 by 2 and the 3 by 3 case, and it's very important that you learn those formulas. But for higher dimensions And for systems of equations that are sort of odd shape, not necessarily square systems, we need a new and more flexible technology. So this was begun by Gauss almost 200 years ago, and it's called row reduction. And it applies to very general systems of equations. So next time we're going to start looking at row reduction and solving general systems of linear equations. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.